And today, we are going to first discuss about the negative binomial mean and variance. If x is a negative binomial random variable with parameters p and r, the mean is equal to r over p, and the variance sigma square is equal to r multiplied by 1 minus p over p square. So we can simply calculate the mean and variance based on these two equations for the case of negative binomial distribution. And this is the example. A website contains 3 identical computer servers, and only one is used to operate the site, and the other 2 are spares that can be activated in the case that the primary system fails. So the probability of a failure in the computer is 0.0005, and assume that each request is independent. So what is the mean number of requests until failure of all 3 servers? Let x denote the number of requests until all 3 servers fail, and let r denote the number of servers with failure. So based on the previous slide, the mu for the case of negative binomial distribution can be calculated by r over p, right? So in this case, the probability p is 0.005, right? 0.0005. And what is r? R is the number of servers with failure. But in this case, we have to find the mean number of requests until failure of all 3 servers. That means r should be equal to 3, right? So this should be 3 over 0.00005. That equals to 6,000. Okay? That is the mean for this example. And what is the probability that all 3 servers fail within 5 requests? So we can calculate this based on this equation, the probability of x when x is smaller than or equal to 5, right? But in this case, the x should be larger than 3 or equal to 3. Why? Because we have to obtain all 3 servers with failure. So this can be the summation of probability of x when x is equal to 3 and the probability of x when x is equal to 4 and the probability of x when x is equal to 5, right? Because x should be equal to or larger than 3. So, based on the previous slide, the negative binomial distribution, the probability mass function can be equal to x minus 1, r minus 1 multiplied by 1 minus p, x minus r multiplied by p r, right? That is the equation for the negative binomial distribution, right? So based on this equation, we can simply change these two. 2 by 2 multiplied by 0.9995 multiplied by 0.00052 3 power, right? 3rd power, right? Because this is the 1 minus p, right? And p is 0.0005. So 1 minus p will be 0.9995. Okay? So in this case, R is equal to 3, right? Why? Because all 3 solvers should be failed, right? So what is the definition of R? R is the number of solvers with failure. So for this question, all 3 solvers should be failed. That means R should be equal to 3, right? And these are the small x, right? Right? So for the first case, R minus x minus 1 is equal to 2, right? And R minus 1 is also equal to 2, right? Multiplied by 0.9995 to, what is x minus R for this case? 3 minus 3, that is 0. So 0th power multiplied by 0.0005 to 3rd power, right? That is R, okay? So this plus, what about this case? That is 3 by 2 multiplied by 0.99952 first power, right? Multiplied by 0.0005 to 3rd power, right? Because the x minus R is equal to 1 here. And the R is not changed. R is equal to 3. That is fixed value. So x is increased, right? So x minus 1 should be 3. Okay? And what about the last one? That is 4 by 2 multiplied by 0.99952 square multiplied by 0.00052 3rd power. Okay? So we have to calculate all these 3 cases. So I'm going to calculate the first case. So this can be, what is 2 by 2? That is 2 factorial over 0 factorial multiplied by 2 factorials, right? Right? So in this case, 2 factorials can be eliminated each other. And what is 0 factorial? That is equal to 1. So this can be 1, right? Okay? And what is 0.99952 0th power? That is also equal to 1, right? So this equation finally should be 1 multiplied by 1 multiplied by 0.00052 3rd power, okay? And this will be 1.25 multiplied by 10 to minus 10th power, okay? So what about this case? To calculate this, we have to first know about 3 by 2, right? That is 3 factorial divided by 2 factorial multiplied by 1 factorial, right? That is equal to 3, okay? And so this equation can be re-expressed by 3 multiplied by 0.9995 multiplied by 0.00052 third power. That is equal to 3.75 multiplied by 10 to minus 10th power. Okay? That is for the second equation. And what about the last one? That is the 4 by 2 can be 4 factorial over 2 factorial multiplied by 2 factorial, right? That is equal to 6, right? So this will be 6 multiplied by 0.9995 squared multiplied by 0.00052 third power. Okay? That is equal to 7.49 multiplied by 10 to minus 10th power. Okay? So finally, this can be 1.25 plus 3.75 plus 7.49 multiplied by 10 to minus 10th power. And this will be 1.249 multiplied by 10 to minus 9th power. Okay? So this is the answer for this question. Okay? And now I'm going to explain about the hypergeometric distribution, which is called 초기화 분포 in Korean. And this can be applied to the sampling without replacement. And a set of n objects contains k objects which are classified as success, n minus k objects which are classified as failure. That means we can simply draw this circle, and this is called large N. And this contains two parts. First one is the K, large K, that is classified as success. Okay? And there is also N minus K, which is classified as failure. Okay? So in this case, a sample of size n object is selected without replacement from the n object, and it contains equally likely probability where the k should be smaller than or equal to large N, and smaller n should be smaller than or equal to large N. So this means that we can select a random sample from this n object, and simply we can assume that this is the small n, okay? Okay? So let the random variable x denote the number of success in the sample n, okay? Then x is called as a hypergeometric random variable. In this case, this part is large x, right? Okay? And this is called hypergeometric random variable. Okay? Because this is the number of success in the selected sample of size n. Okay? So that is the definition. So we have to know about the probability mass function for this case, right? And to understand that, we have to first know about the probability to select this random sample. Okay? So to understand that, we can use the example 3-16. And for this example, the probability that a bit transmitted throughout a digital transmission channel is received in error is 0.1. And let x denote the number of bits in error in the next 4 bits transmitted. And let e denote a bit in error. And let o denote a bit not in error. So in this case, one group is of size x. And contains the error. And the other group is of size n minus x and consists of the trials that are not in error. So this can be, this is the small n, right? And this is the x, and this is the n minus x, right? For this case. And in this case, what is the number of outcomes that result in 2 errors among when n is equal to 4? So, to obtain the number of outcomes that result in x errors, in this case, we can use this equation, n by x, right? In the last class, I was explain about this, right? 그러니까 n개가 여기 전체가 n개 중에서 s개가 지금 에러를 나타내는데 이 x개를 얻을 수 있는 총 아웃컴의 개수는 이걸로 계산할 수 있다 그랬죠. 지난 시간에. 그죠? So, in this case, n is 4, right? And x is equal to 2. So, this will be 4 factorial over 2 factorial multiplied by 2 factorial, right? And this is equal to 4 multiplied by 3 multiplied by 2 factorial over 2 factorial multiplied by 2 multiplied by 1. And 2 factorial can be eliminated each other. And 2 can be eliminated. 2 and 2 is left here. So that's equal to 6, right? So this is the table for the all outcomes that we can obtain from this case. And as you can see, the number of outcomes which result in 2 errors is 1, 2, 3, 4, 5, 6. Okay? So based on this example, we can simply know about the probability of selecting the random sample n is among large n. This is the equally likely case, right? So all the case has the same probability. And the total number of outcomes that we can select the random sample n in large n will be n minus n, right? In this case, what is the probability? Probability is 1 over n by n, right? Okay? Because this case, this is the equally likely case. 그러니까 모든 probability가 다 동일하잖아요. 그러니까 전체 얻을 수 있는 개수가 이거니까 1을 이걸 나눈 게 이게 선택될 확률이겠죠. 그죠? So, this is the probability. And then, the probability mass function of hypergeometric random variable is this equation. And what is the uppercase? That is the number of outcomes that result in X successes in large K object and n minus X failures in large n minus K object. Okay? That is the number of outcomes, right? So the probability mass function for the hypergeometric distribution can be K by X n minus K by n minus X multiplied by 1 divided by n minus n. Actually, for this case, we normally use this equation, right? Simply n by x to calculate the number of outcomes that result in x errors, right? But fundamentally, this should be this equation, right? Why? Because this is the number of outcomes that result in axis error, right? In n sample, right? And this is the number of outcomes that result in n minus x non-error in n minus x cases. Okay? 왜냐하면 저희가 아까도 2, 5를 가졌다는 거는 2를 2번 뽑고 5를 2번 뽑아야 되잖아요. 그죠? 그러니까 에러가 있을 확률 곱하기 에러가 없을 확률을 곱해야 된다고요, 원래는. 이게 총 아웃컴의 개수인데 what is this? That is n minus x factorial divided by 0 factorial multiplied by n minus x factorial, right? What is that? n minus x factorial can be eliminated and this is equal to 1. So this is equal to 1. So this can be, we don't have to consider about this term for this case. But in this case, this is not equal to 1, right? Right? So we have to consider this part. Okay? So I'm going to explain this based on very brief example, okay? We can simply consider this example, and there is a large n here, and it contains A, B, C, D, E, okay? And the number of n is 5, right? And n can be divided in two parts. First one is large K, that include A, B, C, okay? And n minus K include D, E, okay? So the number of K is equal to 3, and the number of n minus K is equal to 2, right? So in this case, what is the probability to select a random sample n? The n should contain 2 from K, 1 from n minus K, right? But we don't know about what is these two and what is this one in this time, at this time, right? So the total number of outcome will be A, B, C, A, B, D, A, B, E, blah, 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 right? We can have any three items from the large N. And what is the number of these? That is 5 by 3, right? Because N is 3, large N is 5. So the number of outcomes to obtain any three items from large N will be 5 by 3, okay? That is equal to 5 factorial over 3 factorial multiplied by 2 factorial. That is equal to 5, 4, 3 factorials by, divided by 3 factorials multiplied by 2 multiplied by 1. And 3 factorials can be eliminated each other. And 2 can be eliminated by dividing 4 by 2. And 2 is left, right? So that means we can have 10 different the sample, right? In this case. And what is the probability to select the 2 in the sample N? We can have A, B, right? We can have A, C, and we can have B, C, right? 이 세 개 중에서 두 개를 선택할 수 있는 가능성은 요게 다죠. 그죠? 그죠? So how can you calculate this? That is simply 3 by 2, right? Because case 3, this part x is 2. So 3 by 2, that is the number of outcomes that we obtain any 2 items from the large K. This is equal to 3. And as you can see, we have 3 different samples, right? And what about this case? We can select only one item from the 2 items. That is D and that is E. Right? Right? So this will be 2 by 1. Okay? That is also equal to 2. Right? So how can we make these 3 items based on these 2 cases? This means that, 그러니까 여기서 A, B, A, C, B, C가 지금 이 석세스라고 가정하고 저희가 만들 수 있는 거는 이렇게 하나, 이렇게 하나, 이렇게 하나, 이렇게 하나, 이렇게 하나, 이렇게 하나죠. 그죠? 이건 어떻게 계산하죠? 이거 2개 곱하면 되잖아요. 그죠? So 3 by 2 multiplied by 2 by 1 is the total number of outcomes that we can obtain 2 successes and 1 error, 1 failure in this case, right? And what is the probability for this case? This is the equally likely case. And this is the all the outcomes that we can obtain 3 items among the 5 items. That is 1 divided by 10, right? So this should be divided by 5, 3. That is the probability, okay? So in this case, that is 6 divided by 10, that equals to 0.6, okay? So there is 60% chance to have 2 successes in the random sample of size and object, okay? So that is the hypergeometric distribution. So we can use this equation to calculate this case, okay? So in this case, the small x should be smaller than or equal to large K, right? And n minus x should be smaller than or equal to large n minus large K, right? And small x should be smaller than or equal to small n. And the small n should be smaller than or equal to large n. That is the requirement to use this equation. And now we are going to solve the example 3-26 based on this hypergeometric distribution concept. And this is the case of sampling with a replacement. 50 parts are defective among 850 parts. And 2 are sampled. Let x denote the number of defectives in the sample. X can be 2. Okay? And use the hypergeometric distribution to find the probability distribution. So this is the examples. So for this case, we can have 2 samples, right? So the x can be 0, 1, or 2. Okay? And in this case, what is the probability of x when x is equal to 2? Based on the previous equation, this can be, to solve this, before solving this problem, we have to find what is large n. Large n is 850, right? What is large k? That is 50, right? And so n minus k is equal to 800, okay? And what is small n? That is 2, right? And what is small x? In this case, small x is 2. So this can be 50 by 2, 800 by 0, divided by 850 by 2. Okay? So we have to calculate all these 3 cases. So there will be 50 by 2 equals to 50 factorial over 2 factorial multiplied by 48 factorials. And that can be 50, 49, 48 factorials over 2 multiplied by 1 and 48 factorials. Okay? So 48 factorials can be eliminated, and 2 can be eliminated by dividing 50. That is 25. So that is equal to 25 multiplied by 49. And that should be 1,200. Okay. And what is the 800 by 0? That is just 1, right? This is 800 factorial over 0 factorial multiplied by 800 factorials. Okay? So this should be equal to 1. Okay? And what is the 850 by 2? That is equal to 850 factorials over 2 factorials multiplied by 848 factorials. That can be 850 multiplied by 849 multiplied by 848 factorials over 2 multiplied by 1 multiplied by 848 factorials. Okay? So this can be eliminated, and this can be eliminated by dividing 850 by 2, and 425 is left. So this will be 425 multiplied by 449. That is 360,825. Okay? So this will be 1,225 multiplied by 1 over 360,825. That equals to 0.003. Okay? And we can use the same procedure, okay? So we can also calculate we can also calculate for these two cases. This will be 50 by 1 and 800 by 1 over 850 by 2, right? And this can be 50 by 0 and 800 by 2 over 850 by 2. Okay? Right? So, if you calculate these two equations based on the same procedure, you can obtain 0.111 and 0.886. Okay? So we can calculate this example based on the hypergeometric distribution. Okay? And this is another example. And example 3-27. A batch of parts contains 100 parts from supplier A and 200 parts from supplier B. And if 4 parts are selected randomly without replacement, what is the probability that they are all from supplier A? And let X denote the number of parts in the sample from supplier A. So this case, we have to calculate the probability of X when X is equal to 4, right? Because we have to find the probability since when we select only 4 parts. 그죠? 4개를 선택하는데 그 4개가 모두 다 supply A에서 와 있죠. 근데 X가 supply A에서 온 파트의 개수잖아요. 그러니까 X가 4가 되겠죠. So, in this case, what is large N? It is 300, right? And what is large K? That is 100. So N minus K will be 200. Okay? And small n is equal to 4, right? And small x is equal to 4. So this can be 100 by 4, 200 by 0 over 300 by 4. Okay? So what is 100 by 4? That is 100 factorials over 4 factorials multiplied by 96 factorials. That is 100 by 99 by 98 by 97 by 9 factorial divided by 4 by 3 by 2 by 1 by 96 factorials. So this can be eliminated, and 4 can be eliminated by dividing 100 by 4, and 25 is left. And 3 can be eliminated by dividing 99, and 33 is left. And 2 can be eliminated by dividing this, so 49 is left. So this can be 25 multiplied by 33 multiplied by 49 multiplied by 97. That is equal to 3,921,225. Okay? And what is the 200 by 0? That is equal to 1, right? And what is the 300 by 4? There will be 300 factorials over 4 factorials multiplied by 296 factorials. This can be 300 by 299 by 298 by 297 by 296 factorial over 4 by 3 by 2 by 1 by 296. So this can be eliminated. Eliminating 300, that's 75 is left. And 3 can be eliminated by dividing this. 99 is left. And 2 can be eliminated by dividing this. So 149 is left. So this will be 75 multiplied by 299 multiplied by 149 multiplied by 99. So that is equal to 330,791,175. That is too much, right? So this will be 3,921,225 multiplied by 1 divided by 330,791,175. So they should be 0.0119. Okay? So this is the answer for this example. And in this case, what is the probability that 2 or more parts are from supplier A? That is the probability of x when x is larger than or equal to 2. Right? So this will be the summation of the probability of x when x is equal to 2 and the probability of x when x is equal to 3 and the probability of x when x is equal to 4. So this will be 50 by 2, 800 by 2, 850 by 4 plus 50 by 3 and 800 by 1 and 850 by 4 and 50 by 4 and 800 by 0 over 850 by 4. Okay? So this will be 0.298 plus 0.098 plus 0.012, okay? And that is 0.408. Oh, sorry. Yeah, this should be back 100, right? This should be 200. This should be 300, right? And this should be 100. And this should be 200. This should be 300. So this is the corrected answer for this question. So the probability of x when x is larger than or equal to 2 is 0.408. 오케이? 공학용 계산기 다 있으시죠? 그거 들고 시험 보셔야 돼요. 아시겠죠? So this is another example. And what is the probability that at least one part is from supplier A? This indicates that the probability of x when x is larger than or equal to 1, right? But to calculate this, we have to calculate the probability of x when x is equal to 1 plus the probability of x when x is equal to 2, the probability of x when x is equal to 3, the probability of x when x is equal to 4. That is too much, right? So this can be re-expressed by 1 minus probability of x when x is smaller than 1. right? Because x is integral here, so we can simply change this equation to this. And this can be 1 minus probability of x when x is equal to 0. Right? So, what is this? That is 100 by 0, 200 by 4 over 300 by 4. Right? And this can be, this is equal to 1, right? 1 multiplied by so this is 1 multiplied by 64,684,950 over 330,791,175. So this will be 0.196. Okay. So the final answer will be 1 minus 0.196. That is equal to 0.804. That is the answer for this question, okay? And now, I'm going to explain about the hypergeometric mean and the variance. If x is hypergeometric random variable with parameters large n, large k, and small n, then the mean is equal to n multiplied by p, and the variance sigma square is equal to n multiplied by p multiplied by n minus p multiplied by n minus n over n minus 1. Okay? That is the definition. And this is the binomial variance, right? And in this case, the probability of success is large K divided by n. Okay? So when n over n becomes very small, which means that large n is much, much larger than small n, the variance sigma square approaches the binomial variance, right? Why? Because when large n is much larger than small n, that can be approximately n. And this also can be approximately large n as well. So this can be eliminated, so this is equal to 1. Okay? So when large n is much larger than smaller n, the variance for the hypergeometric distribution is identical to that of binomial variance. So this is the example. And in this here, the large n is 50 and small n is 5. Large n is 10 times larger than the smaller n. Okay? So when we calculate some example based on these two distributions, that is the hypergeometric probability and that is the binomial probability. And as you can see, for distributions exhibit the similar behavior, which means that we can simply use the binomial distribution concept when the larger x is much larger than the smaller n. Okay? So I'm going to explain why it is important. And this is another example. There are 1,000 customers, and among them, 700 have purchased at least one of the companies in the last 3 months. To evaluate a new product, 50 customers are sampled randomly. Okay? And what is the probability that more than 45 of the sampled customers have purchased in the last 3 months? Let X denote the number of customers who have purchased product from the company in the last 3 months. Then X is the hypergeometric random variable with large n is equal to 1,000 and large k is equal to 700 and small n is equal to 50. So in this case, we have to calculate the probability of X when X is larger than 45, right? That is the example. Because we have to find the probability that more than 45 of the sampled customers. So this can be the summation of X from 46 to 50 by what is large n, large k, that is 700 by X, okay? Large k is 700 here. And what is large n minus k, that is 300 by n is 50. 50 minus x, right? Over 1,000 by 50. Okay? So we have to use this equation. And we have to calculate all these cases. Right? And for example, I'm going to solve just the first case, okay? There should be 700 by 46, 300 by 4, 1,000 by 50. Okay? So for this case, we have to calculate all these three cases in here. And what is 700 by 46? It will be by over 46 factorial multiplied by 650 factorials. Right? There will be 700, 699, blah, 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 654 factorials over 46, 45, 1 multiplied by 654 factorials. That is too much, right? It is very difficult to calculate this equation. So in that case, it is almost impossible to calculate this by hand. So we can simply use the binomial distribution concept. Why? The n, large n is equal to 1000 and small n is equal to 50. So in this case, large n is much larger than smaller n, right? 큰 n이, 전체 n이 조그만 n보다 훨씬 크죠. 그러면은 바이노미얼 디스트리뷰션을 쓸 수 있다 그랬잖아요. 그러니까 approximation으로. So it is almost impossible to calculate, to solve this problem by hand. So since small n over large n is very small in this case, the binomial distribution will be used to approximate the hypergeometric distribution. So in this case, the probability is large k over large n, right? That is equal to 0.7. So this can be changed to the binomial distribution case. That should be the summation of x from 46 to 50 and 50 by x multiplied by 0.7 to x power multiplied by 1 minus 0.7 to 50 minus x power, right? That is the definition of the binomial distribution, okay? So also, in this case, we have to calculate all these cases. But it is much simpler than the previous case, okay? So I'm going to solve this one first. The probability of x when x is equal to 46, that is 50 by 46 multiplied by 0.7 to 46 power multiplied by 0.3 to 4th power. And this will be 50 factorial over 36 factorial multiplied 4 factorial. Okay? This can be 59 by 47 by 46 factorial over 46 factorial by 3 by 2 by 1. The 46 factorial can be eliminated and 4 can be eliminated by dividing 48. 12 is left, and 3 multiplied by 2 can be eliminated by dividing 12. 2 left. So this will be 50 multiplied by 49 multiplied by 2 multiplied by 47. That is equal to 230,300. Okay? So this will be 230,300 multiplied by 7 to 46's power 0.3 to 4th power. So the answer will be 0.0014. But I know that this is also complicated, but as compared to the previous hypergeometric distribution, this is much simpler, right? So when you think that it is almost impossible to solve the problem by hand, for the case of hypergeometric case, you can simply use this binomial distribution when large n is much larger than smaller n. Okay? There's no requirement. That is dependent on your choice. But based on the previous slide, when large n is larger than smaller n by 10 times, we can simply use the binomial distribution. Okay? 뭘 써서 풀라고는 안 줄 거예요. 네. 10배 정도 차이 나면은 바이노미얼로 풀어도 돼요. 네. 근데 혹시 시간이 있거나 손으로 풀 수 있는 정도면 이거 하이퍼지오메트릭을 쓰는 게 정확한 값을 얻을 수 있겠죠. So, we all understand about what is hypergeometric distribution today, and when we can use the binomial distribution instead of the hypergeometric distribution, right? So, for the Poisson distribution, I'm going to explain this on the next Wednesday, okay? So this is the end of today's class. So please submit your first homework by the next Wednesday, okay?